Not all goods produced are intended for immediate consumption. Rather, they are produced as inputs to other production processes, such as Solvay's soda ash. The production of inputs is known as intermediate production. Intermediate and final production activity generates a vast interconnected system of firms and industries and significant infrastructure to support that system. This worldwide economic structure has many implications, and I'm going to describe two that have particular salience for complexity systems thinking. The first is the emergence of supply chains and the requisite infrastructure that supports them. Supply chains yield naturally to network modeling, and networks generally get complexity scientists excited. Supply chain networks have the added benefit of a geographical basis, which aids in the interpretation and translation of network-based observations. A preliminary paper describing global phosphorus flows is in your optional reading list. Supply chains also pose interesting intertemporal coordination problems. The beer game, otherwise known as the production distribution game, is a well-known demonstration of the challenges of supply chain coordination. It's an actual game, so let's see a demonstration.
Place the weekly order cards in the order card box. Give each player their matching pad of paper. Take 2 pieces of paper from each pad, write the number 4 on them, and place them face down in the orders placed in incoming orders boxes. The factory only needs 1 piece and places it in their production request box. Put 12 chips in the current inventory and 4 in each of the shipping delays. The retailer sells beer to the customer. The wholesaler sells beer to the retailer. The distributor sells beer to the wholesaler, and the factory produces beer for the distributor. Each position slides their chips at the same time by placing each hand on a shipping delay box and sliding the chips over one box. The retailer looks at their weekly order card and then takes the needed amount of chips from their current inventory and pushes them up to the customer. The distributor and manufacturer do the same thing. They look at their incoming orders, push the needed amount of chips to the shipping delay, and then slide the orders placed slip to the incoming orders box. The factory checks the incoming orders and pushes the number of cases to the shipping delay. Then they also have to check their production requests and put that number of chips into the production delay from the raw materials. To place orders, you write the amount of cases you would like to receive and place the slip face down in the orders placed box. The retailer, wholesaler, and distributor all do this the same way. To place orders, the factory writes their desired number of cases on the slip and places it in their production requests box. The last step is to fill out your form, and each position does this the same way. Write down the number of cases you have in your current inventory, any amount of backlog you may have, and the number of cases you requested.
And here are some results from playing the game. Each column shows the results from 4 distinct games, each named after a brewery. The top set of graphs represent orders, and the bottom set inventories. Within each set of orders or inventories, the first graph is a time series of the retailer's order or inventory, the second the wholesaler, the third the distributor, and the fourth the factory. Note the oscillations and the amplifications of those oscillations as we move along the supply chain from the brewery to the store. The beer game describes the supply chain from the factory to the retailer, but most of intermediate production occurs in producing and collecting the inputs to production. Wassily Leontief constructed the first economic computational model in the mid-1960s with what are known as Leontief input-output matrices to describe the intermediate production process. The matrix consists of all industries, also known as sectors, along the rows and columns, and a value at the ij location is the quantity of inputs from sector I used to produce goods in sector J. Each column can be totaled to calculate total inputs for a sector. There's another column, the open sector, which are goods not used for intermediate production but for final consumption. Thus, the sum along row I should account for all the internal demand for sector I from both intermediate and final production. Exports are considered a separate matrix. Keep in mind that based on what our institutions actually measure, these quantities are measured in dollars rather than physical units, and it's not always straightforward to recover physical units from prices and exchange rates. The model uses a transformed version of the input-output matrix called the consumption matrix, which is each of the elements divided by the column total, which gives all the input quantities required for $1 of sector output. The computation solved for the equilibrium level of sector production, X, a vector of all industry production values, such that X equals C times X plus D plus E, where C is the consumption matrix, D is the open sector vector, and E is the exports vector. The Leontief model is based on a square matrix with a single type of entity, which was a sector. Next, we're going to use a similar construct to explore multiple types of entities, in this case, interlinkages of countries and products, with which we can construct a global product space. We're going to work through the calculation of something called the Economic Complexity Index. Using worldwide export data, we can create a product space as a bipartite network with nodes consisting of either a country or a product. Countries have a collection of products they export. Export data is used because it exists, though production for both domestic and export may be more meaningful, and that product can be more or less unique to the exporting country. The links between countries and products are weighted with how much of a given product the country produces, but really from the data is how much it exports. We're going to now find the revealed comparative advantage, RCA, otherwise known as the Balassa Index, for all country and product combinations. We can answer that by looking at the exports of P by country C divided by all exports by country C, all over all exports of product P divided by all exports globally. So mathematically, we can write the RCA as the weight for country C product P divided by the summation over all products for country C, divided by the weight of all countries, all products, or for product P, divided by the sum of all products, all countries, to get total exports. Next, I'm going to construct an adjacency matrix representation of the bipartite graph. I'll call it M. But I'm going to modify RCA values such that I'll only include linkages with an RCA greater than or equal to 1 and change those values to 1. Now I'm turning my weighted graph into an unweighted graph, so only those linkages between country and product with relative comparative advantage are captured. So I'm going to randomly populate my M matrix with 1s and 0s. Remember, countries are rows and products are columns, so if there's a 1 between a country and a product, that means that they're linked with a relative comparative advantage. And then a 0 means either no linkage or an insignificant linkage. And now we've captured the entire bipartite network into an adjacency matrix. Theoretically, some products are considered to be more difficult to produce than others, requiring more knowledge and technical infrastructure to successfully manufacture. The question is whether or not it's possible to capture something about the economic complexity of a country from just the export data. The method of reflections for bipartite graphs, pioneered by Cesar Hidalgo et al., is a network analysis method intended to reveal hidden network structures. Let's apply this to a graph using our adjacency matrix representation. First, we calculate the zeroth order reflections, known in this context as diversity and ubiquity. Diversity of the country's export bundle is the sum along each country's row and is notated as K sub C. Ubiquity of a product is the sum along each product's column and is notated as K sub P. Now we're going to add iterative notation, and we're going to specify that this is the zeroth order reflection. So we have diversity of C is going to be K sub C and then 0 for the zeroth order, and the ubiquity of P is going to be K sub P with a 0 for the zeroth order. For further reflections, we calculate them as K sub Cn for the nth reflection is going to be 1 over Kc0, which is the diversity, summation over all products for the matrix element for the country for the product that you're currently summing, times the Kpn-1 term, which is the product reflection from the previous time step. Likewise, the reflection for the product at reflection n is 1 over Kp0, which is the ubiquity, summed over all countries of the matrix element for the country times product. And then you have the term Kcn-1, which is the previous reflection term for the country. It's called reflections because each country's term is based on the previous value of the product's term, and vice versa. And it's iterative because it uses previous values to find the current values. So let's exercise this formula and try it out for n equals 1. So for country C, Kc sub 1 is going to be 1 over the Kc0, which is the diversity, and then we're multiplying by MC1 times K for product 1, which 0, which is going to be the ubiquity of product 1, matrix element C2 times the ubiquity for product 2, plus matrix element C3 times the ubiquity of product 3, etc. Now notice that if we were using n equals 2, we'd actually be using this first iteration instead of the zeroth iteration, because we're going to n-1 and we're counting n. We end up with the zeroth term, and the zeroth term have lovely names like ubiquity and diversity that I can just say, so it's easy. So for the product term, it's going to be very similar. It's going to be 1 over K sub P0, which is the ubiquity, and then it's going to be the matrix element times the diversity for country 1, matrix element 2P times the diversity of country 2, matrix element 3P times the diversity of country 3. Here's a plot of 18 reflections for a set of countries. So you see that the reflections are on the right-hand side. So if you turn sideways, you can see you've got KC0 all the way to KC18. So these are reflections in terms of the countries. So we have on the very top, we've got a list of countries all the way across. And then you see these colored lines go from one spot to another spot. So here's what we've done. We've said here are the ranking of all the countries according to their diversity. So now what's been done for the 18th reflection is, again, we've ordered the countries from the highest value for that 18th reflection down to the lowest value of the 18th reflection. So we notice a couple of things. We notice that the values stop changing, so they kind of even out after several iterations, and they settled to a value that we are going to call the economic complexity indicator. And we're going to notice a couple of other things. So these countries have similar diversities. So Pakistan, Chile, and Singapore have similar diversities because they're all clumped together on a diversity rating. Don't forget, diversity rating is just the 0th reflection. But by the time we get to the 18th reflection, we see that they've actually spread out a bit, and so there's a lot more variation. And here's something super curious. Once you look at the ranking for the 18th reflection, you realize that that correlates very strongly with GDP. But what does the 18th reflection actually mean? Nobody knows. It's completely esoteric. But the assertion is that the ECI reveals something about the complexity of that country's production, and that higher complexity leads to higher GDP. If you're curious about this, the Hidalgo paper from which the study was taken is in your reading list. Another Leontief variation, also with a bipartite network, is exploring industry and occupational co-occurrences. Here are plots of industries along rows and the occupations along columns, where each element, ij, is the presence of occupation j in industry I, such that the Balassa index for that co-occurrence is greater than or equal to 1. Each matrix in this 4-panel graph represents a southwestern state: Arizona, California, Colorado, and New Mexico. Note the obvious differences in the matrices, which indicates that such graphs could be used as fingerprints or genomes representing various industry occupation structures, and changes in these structures could be measured via network metrics across time.